All right, this is 0654 summer 19 question paper 4.1. We're looking at question 9, physics question. This is our graph drawing question. I've deliberately not done this yet because I want to show you the process we use to go through this. This question is a bit of a lesson on question reading. Okay, you're told some information about the experiment. You're told that we've got the feather and hammer released from the same height at the same time. Okay. And then we were told this really important bit. They both fell for 1.3 seconds. Now, if you don't read that bit, there's a chance you might lose a mark. Because I am not allowed to plot anything beyond 1.3 seconds. And you see down here, this is 1.2, 1.4. Okay, so 1.3 is somewhere in the middle here. It would be worth your while, using pencil, obviously, to do something which just allows you, it's not very clear on your screen, but I can see it very clearly here. I'm not going to go past that mark. Okay. We need to now draw our line. Okay, it should be a straight line because we're following here with constant acceleration. How do I know that? Well, we're assuming here that the moon has no atmosphere. Okay, as a result of that, then the acceleration on the moon is just going to be equal to g. Okay, that's going to be important for later. Now, what we now need to do, obviously we need to draw a straight line because we've got a speed time graph. If I've got constant acceleration, that means I have constant gradient. I'll just write that down to remind us. Constant A, therefore, manifests itself as constant gradient. And so therefore, a straight line. Now, the line should be straight, but where does it go? Here's a little point that I think would be quite nice. We know that A is equal to G. We know that G is equal to 1.6 meters per second squared. Okay. So in order to know this, I know I need to draw something. Yeah. It should start from 0 because I'm not moving. All right, at the beginning, but it's got to go somewhere, and I don't know where it's going to go. Okay. It's going to pivot around this. How do I know? Well, I can use my equation for acceleration. A equal to v minus u over t. Now u is down here is equal to 0. So really, I've got v over t. Okay, where v, t are some finite points on the graph. Now I could ask myself, what values do I know? I know that a is 1.6. But then I'm going to choose a time value. And what I'm just going to do very simply is I'm going to choose time equal to 1. Okay, why would I do that? Well, that allows me to know the points on my graph. What I'm going to say is I want to know the value of speed v at 1 second. Well, if a is equal to v over t, then v is just equal to the product of a and t. I've got 1.6 times 1, and so therefore that is 1.6. So after 1 second, my speed should be 1.6. Okay, if I come here, get to this point, okay, this is 1.6 right here. Again, I've got to use my very carefully. Okay, 1 second, 1.6. And that is the bit that allows me to draw my line. Okay, because without 2 points, you cannot draw a straight line. Make sure that I'm going round through there. Nice straight line through there. Okay, so just be careful when you're plotting a graph. It might look like an easy one at the start. However, it's actually a bit more convoluted, and you do need to worry about where your lines are going. My 0 point there is probably a bit out there. I need to make sure it goes right through that origin. Okay, we're then asked, what happens if the experiment were repeated on Earth? This is where you need to think a little bit about your own experience. The two answers we're looking for are that if we took this experiment on Earth, you would notice that the hammer would fall very, very quickly, and the feather would take very, very long to fall. Now the reason for that is twofold. Gravity on Earth is much bigger. Okay, on Earth, if we go to Earth, we're making that multiplied by 10, by 6, sorry, to equal 10. But the other difference is that Earth has an atmosphere. And so as a result, we're going to have air resistance. Okay? So let's think about this in a little bit of detail. Okay, the first difference we would notice is that the hammer would take a shorter time to fall. And the reason for this is that the weight on Earth would be much greater. Remember, we've got our equation, okay, W equal to mg. G goes up, and so therefore W goes up. Remember, the mass stays the same. Okay, well, our hammer, we've got to assume, is going to experience some air resistance. Okay, but that air resistance is going to be so small compared to its weight, yeah, that it's going to fall very, very quickly. However, the feather, again, you should be used to this just from your daily experience. If you see things like feathers fall, they take a long time. All right, the reason for this is that they've got a large air resistance acting on them. Okay, remember the feather has a small weight. Okay, W is very small. So if we're thinking about force body diagrams for these two situations, if we've got my hammer up here, okay, it has a large weight and a small air resistance. And really, on my feather, really what happens is at the beginning, well, after we've equalized everything, those weight, well, initially our air resistance is very, very big, like on a parachutist, and then as things slows down, eventually those values will balance each other when we hit terminal velocity. Don't worry too much about that. Really, the idea here being is everything's relative. Yeah, for the hammer, I've got a large weight and a relatively small air resistance. For my feather, it's the other way around. And this is all because we're suddenly in an area with a higher gravity and also a larger atmosphere and therefore larger air resistance. Okay. Think about our astronaut and the clothes they're wearing. Okay, lucky us. This question, you should be starting to get used to these. These are questions about radiation. Okay, the main method of energy transfer, thermal energy transfer in space is radiation. The reason being that there's no particles, there's no atmosphere. If there's no particles, there's no way of conduction or convection from happening. Okay, so the reason that we wear a white suit, remember white is a good reflector, black is a good absorber of radiation. The reason we wear a white suit is to avoid overheating. The explanation, therefore, the white suit is a good reflector of the sun's radiation, meaning that they won't heat up, they'll stay cool. And there's a similar reason for why if you go to Mediterranean countries, a lot of houses there are painted white. That's to keep them cool. Okay, we're then talking about ionizing radiation. Key thing, if you see ionizing radiation, what does it do to the human body? It causes cancer. Okay, anything to do with cancer here would be good. Remember cancer, a good answer. Anything related to that would work. Remember our ionization and our ionizing radiation causes the breakdown of the cells such that they reform, and they reform sometimes into these tumors, cancerous tissue. Last one. Okay, we're now doing a little bit of our equations. This is our balancing our reactivity, our radioactivity. We've got our plutonium. You're told its mass number, nucleon number, or atomic number, proton number, 94. And remember, everything on the left-hand side must balance everything on the right-hand side. Okay, so you're told alpha. Try and remember that alpha is just a helium nucleus. Yeah, 2 protons, 2 neutrons, and therefore 2 and a 4 on the top. You've got your 4 and 2 here. Anything on this left-hand part must balance with that. So 239, take away my 4, 235. 94, take away my 2, 92. And it's at this point where you try and remember what the atomic number, how that relates. Remember, that tells you the element that you're looking at. You need to go into your periodic table, which is at the back of the paper, find 92, and you will see that that is uranium.